Let's see, yeah, we're going. Okay, so first I'll start with any questions that you might have over anything that we talked about last time or mini exam question. I mean, I'm not going to go over the mini exam, but anything general. No. I did send out an email about 15 minutes ago that contains your second mini exam, and it's due 2 weeks from today. So it's only 5 problems, but you read the instructions. You're not allowed to work together on that one. So, if you get stuck or you need help, please make sure you reach out to me directly. All right. Okay. All right. Let's get started. So it's actually, kind of a good thing that we are going to be doing this Zoom because there's a lot of animation type things that I want to be doing today. And of course I could do it in the class, but here, as long as you can see my shared screen pretty clearly, it's probably better than it would be in the classroom. So with that said, let's get going. All right, we are continuing 10.5 today. What we had done last time, we had finished out the vector equation of lines, right? And the last thing we did in class was to look at 2 different lines and determine whether or not they were, to show that they were skew, right? So we're now going to continue this section and talk about planes. And we briefly at the end of class said, if you have a plane, let me also remind you, or tell you, I uploaded the videos from last class to YouTube, and then I forgot to publish them. So I just published last class's videos like a little while ago. So I apologize. If that happens again, just someone shoot me an email or a text or something saying, hey, the videos aren't up. Usually I get them up that same day. So if it's the next day or day after and they're still not there and you're looking for them, just remind me. Okay, so we had talked at the end of class about a plane, and we said that to define a plane, we need 3 distinct points. And I think everyone bought into that. We looked at it with that little wooden XYZ that I had in class. So we're gonna look further into this and see if maybe there's another way we could define a plane, or maybe we need not less information, but not necessarily 3 points. Just like with a line, we could have 2 points, or we could have a point in a direction vector, right? Those are the 2 different scenarios. So with a plane, 3 points would suffice, but maybe there's something else. So let me show you here this animation. We've got this plane, right, living in 3-dimensional space, and we have 3 points on that plane. So what I'm going to do first is I'm going to create 2 vectors that go from 1 point to the 2 other points. That we can do. We've been doing that for a while, right? Create 2 vectors. Both of those vectors would be considered to be parallel to the plane because they point in the same direction, or they lie within the plane, right? So vectors that live on the surface of a plane are parallel to that plane. So both of those vectors are parallel to this plane. And now what I do is just compute the cross product of those 2 vectors. And if I compute the cross product, I'm going to get a new vector, the purple vector, and that vector has the property that it should be orthogonal or perpendicular to both of those red vectors, which in turn makes it orthogonal to the plane itself. No matter which way I look at this, that purple vector will be perpendicular to the plane. So that leaves us with a question. Let me see. I don't know if you can see me very well, but maybe if I stop sharing. If I stop sharing, does it show me bigger?
Yes, it did.
Yes?
Yes.
Okay. So if I have a plane, I had my plane sitting here a little while ago. Notice use this. If I have, let me turn off my background thing because it kind of hold on. I do not want to blur my background. Sorry. I want no background. Where is that? There it is. Okay. Okay. So if I have a plane sitting here in 3 space, then of course I could have 3 different points and that would define the plane. But how about just 1 point and that vector we were just talking about? Would that be enough? So if I have just a point like my fist sitting in space, there is an infinite number of planes that would go through that 1 point. But if I then tell you that it's not only a point, but it's also a vector that is orthogonal to the plane or perpendicular to the plane, can you convince yourself that there's only 1 plane that would actually do that, that would satisfy that criteria? Yes, I'm seeing shaking of heads. Good. So that's really the conclusion of this. Let me see, where am I? There we go. Sorry, I might accident. Okay, there we go. Y'all see my screen again? Yes. Okay. So that's what this whole little section starts with about planes, is that yes, 3 points are good, but 1 point and a vector that's orthogonal to the plane, we call that vector the normal vector to the plane. All right, so that's what I summarized that whole thing right here. I'm not going to read through it. So here's the conclusion. It turns out that all we need to define a plane is a point on the plane, any point on the plane, and any normal vector to the plane. So remember, when you do a cross product, the order that you do the cross product matters, right? So if you did that, those 2 red vectors that I had, if I crossed them the other way, right? If I would have crossed these 2 vectors the other way, this purple vector would just be pointed out the other side of the plane, but it would still be orthogonal to the plane. So there's not a unique normal vector. It's any scalar multiple of that purple vector would qualify as being a normal vector to the plane, which is why I say here, any, right? Any normal vector to the plane. As soon as you have that, you've defined the plane. So let's get deeper into this. Let's say we have the actual point. All right, so somebody gives us a point, x0, y0, z0. Okay, we got this point on the plane, and they give us the normal vector. So that's provided to us. Somehow someone gives it to us, right? We have that normal vector. Then we can come up with the equation of the plane. And this equation of this plane should be something that looks familiar to you a little bit, right? You may remember seeing something like that in college algebra or somewhere else. That is the generic equation of a plane formula, where the x0, the y0, and the z0 are just the x, y, and z component, sorry, not components, coordinates of the point on the plane. And then here's the big thing. The A, the A, the B, and the C, which turn out to be the coefficients of the variables x, y, and z respectively. Those coefficients will always be the components of the normal vector. All right, so I'm going to give you an example, but I'm trying to kind of like state it first. By just looking at the equation of a plane, we're going to be able to recover the normal vector very easily. So I go on to say here that, notice that this equation of a plane that I'm putting here in front of you is not a vector equation. Last class, we talked about the vector equation of a line. Here, we're talking about the standard equation of a plane. Later on this semester, we will talk about the vector equation of a plane, but that's to come. Stay tuned. All right, now taking this equation here that I have in blue, if you actually go and distribute the A through the parentheses here, and the B through the parentheses, and the C through the parentheses, right? Then you're going to get this equation. And I just rearrange things there. I put all the X, Y, Z stuff on the left side, and I did the X0, Y0, Z0 stuff on the right side. If I rearrange that, that's what it'll look like. And then finally, if we just take all of this right here and realize that that should all just be a number, because A is a number, X0 is a number, B is a number, Y0's a number, C is a number, Z0's a number. So all of this together is just a number. If we call that number D, then we can replace all that stuff and we get the equation that you're used to seeing in, you know, college algebra or linear algebra or something like that. So let me give you a specific example right next to this. Let's say I write negative 3x plus 2y equals, not equals, sorry, minus z plus 10 equals 0. Okay, we would look at that and we would realize from looking at this that this is the equation of a plane. And then we could, if we wanted to, identify the normal vector of this plane. So what would be the normal vector for that plane? Oh, let's see how this goes. So someone's going to raise their hand, I guess, or chat it. Where did my chat go? My chat box disappeared. Oh, there's a hand. Sorry, I didn't see it. Go ahead, Jonathan.
It would be -3, 2, and -1.
Yeah, it's very simple, right? It's just the coefficients in front of x, y, and z. That's it. That's all it is. That's your normal vector, right? Now, how about could somebody get me a point? Because remember, to define a plane, we needed a point in a normal vector, right? Right now we have the normal vector. Who wants to tell me how you could get a point on that plane? I just need one. Go ahead, Hunter.
Could we just solve that for 0?
How do you mean
So-
solve it for 0?
solve our equation. So we just need to work out a set of numbers that would work.
Okay, yeah, we need to just
So we would
figure
solve
out.
for any 0.
We need to satisfy the equation with any x, y, and z we can come up with, right? We just need to figure out an x, y, and z that's going to make that equation up there true. So I don't know. I'm just kind of looking and inspecting. How about we make x 0? Sorry, yeah, we'll replace the x with 0 in this equation. And let's replace you want to go y with 0 as well? Let's do that. Y is 0. And then that would leave me with this equation right here, which is basically just negative z equals, sorry, I didn't put the minus, plus 10 there, plus 10 equals 0. And we just solve that for z and you get z is 10. So this is a point on the plane. So for this little example, what I did is I gave you the equation of the plane, right? And from that, you were able to generate the normal vector and some point on the plane. You could find infinitely many other points. That's just one that I chose to do, right? Let's go the other way around, right? Let's see if we can't figure out the equation of a plane. I'm not going to do that example yet. Let's do this. I'm going to give you a point, and I'm going to give you the normal vector, and let's come up with the equation. All right, so let's say I tell you that you have this plane. I tell you that the normal vector is the vector, let's go with -3, 5, 1. And I tell you that a point on that plane is the point -1, 2, 3. Find the equation of the plane. So all I would do is just go to my generic formula, right? My generic formula would be A, x minus x naught, plus B, y minus y naught, plus C, z minus z naught equals 0. And just remember that these numbers over here are the x naught, y naught, z naught, and that these numbers here on our normal vector are the A, B, and C respectively. This is not, I mean, this is not difficult calculus, crazy stuff, right? This is just like, you got the formula, let's just plug things in. There's nothing magical happening here. There is something interesting though, we'll talk about in a moment. Let me just replace things. -3, x plus 1, because you have a double negative there, plus 5, and then y minus 2, and then plus 1. I don't need the 1. I'll write it anyway. And then z minus 3 equals 0. So that is our equation of that plane. Now, what we normally like to do is distribute those coefficients or those numbers through. So I'm going to go ahead and do that now. So if I distribute, negative 3x minus 3 plus 5y minus 10 plus z, take away 3 equals 0. Then I'm going to collect all my x, y, z's together on the left. 3x plus 5y plus z, and then put all those numbers together, negative 16 equals 0. There we go. And that looks more like, again, what you would see had you, if you're in some other class, right? So, all right. Would it have, I told you, remember that when it comes to the normal vector, it's not unique, right? It's not unique. So I could have, instead of using this normal vector, right, this one here in yellow, instead of using that one, I could have used any vector that is parallel to that vector, right? Anything I want. Would that change the equation of the plane? What do you think? Shake your head, yes or no. What do you think? If I change the normal vector, does this equation at the end change? I'm seeing some no's and some yeses. Let's see, let's try. Let me use a different normal vector. Let me scale it, okay? So I'm gonna take a different normal vector, and all I'm gonna do is, let me double everything. Negative 6, 10, 2. That would be a normal vector, wouldn't it? It would still be normal because it'd be parallel to the one we just had. So if you were to use those numbers instead into this, right, you would get negative 6. I'm going to kind of go a little faster, x plus 1. We're using the same point, right? And then we would get plus 10, and then y minus 2, and then plus 2, and then z minus 3 equals 0. Distribute through. And then move all your x stuff and y stuff together. What is that, minus 32? There's my equation, right? Any questions on how I got that? Okay, so are they the same equations? They look different, right? They look different, but they're multiples of one another, right? Like I could take this equation right here and multiply it times 2, and it's exactly this, right? Or you could say the other way around. You take that equation, divide by 2, and you go back to that one. The only reason we can do that is because we have equals 0. So no matter what we multiply on both sides, we're always going to get 0 on the right-hand side. So the equation maintains its form. How about if we change the point? What if we keep that normal vector as the original yellow one? If I change the point, will it change the equation? What do you think? I'm relying on your head shakes right now. If I change the point, do you think it changes the equation of the plane? I'm seeing, again, some yeses and some nos. It actually turns out that it does not matter, which is a little weird because we could pick any point that lives on that plane, right? Now, I'd have to find enough. Let me say, sorry, I should have phrased that differently. The equation will stay the same, all right, as long as I'm picking a point that is on the plane. Like if I pick just a random other point right now, I might be talking about a different plane. But if I pick a point that was on that plane, then the equation should stay the same. So I'm going to leave that just as a fact and not go through it. If you'd like to see that worked out, I can work it out, outside of class. All right, back to the notes. All right, so we have the equation plane. Let's do this example here. This will kind of force us to go through all of the steps. We want to find the equation of a plane through through 3 points. So I give you 3 points in 3-dimensional space, and we're trying to find the equation of the plane through those 3 points. So I'm going to do exactly what those notes showed a second ago. I'm going to have those 3 points in space. I'm going to create a vector that goes from, one point to the other, and then another vector that goes from there to there. Let's call this one U. Let's call this one V. And then once I figure out what those vectors are, I'm going to find the normal vector of this plane by taking the cross product of those 2 vectors, right? And that'll get me my normal vector. And then once I have that normal vector, all I'm going to need is a point, right? All I'm going to need is a point. Well, I actually have 3 points. I can pick any of these, all right? So why don't we, I want to speed this up a little bit. Let's create the vector U and V first, and then I'm going to use some technology to do the cross product. All right. So I'm going to label my points right now. This is the point 1, 2, 14. This one's going to be -2, -5, -1. And this one's the point 12, -3, 1. And if I do that, then the vector U is the vector that goes from here to here. Well, let me do something real quick. Mouse. Pointers. All right, I changed my pointer so that you can see it a little bit easier. I'm going to take the vector that goes from here to here, so I subtract, and I should get a vector -3, -7, and -15. I'm already thinking that sucks because I'm going to have to do a cross product. These numbers are going to be kind of big. Then the vector that goes from that point to that point, I do subtraction again. I get 11, -5, and -13. Okay, any questions on those, on that? I'm going to cross them now. Now, I told you that on exam, on the midterm and final, you're allowed to use your calculator to do cross products. But that means you need to learn how to do a cross product on your calculator. And if you don't know how or you need help, just get with me on that. For this today, what I'm going to do is, I already did this before class. I went to Wolfram Alpha. And all I did is I typed in up here cross, and then they don't use, it'll take it even though there's parentheses, and it looks like these are points. It knows I'm trying to cross 2 vectors. And are those right? Did I put those the right numbers? Make sure I didn't mess that up. Yeah, that should be right. Okay. So I asked Wolfram Alpha to cross it. It said, okay, yeah, I'm going to do a cross product, and it returned this vector right here. So I'm just going to slap this in here for us. So the result is that our normal vector is the vector, see, I'm going to write it as a vector though, 16, -204, and then 92. And that is a massively long vector, right? So I can use that vector, or I can use any scalar multiple of it. So I'm just going to look at it real quick and see if there's a number that goes into all of those numbers that divides through. And 2 works, but 4 also works. So I'm going to go ahead and scale the vector. And if I scale that vector, my new normal vector, I'm not going to use that one. Dividing everything by 4, I get 4, -51, and 23. I'm only doing that to keep my numbers small. That's all. You could have stuck with those numbers. All right, that's my normal vector. All right. That's my normal vector. So now I'm ready to go use the generic formula. A x minus x naught plus b y minus y naught plus c z minus z naught equals 0. Now, what I'd like to do is let you have a minute to do this yourself. And what I'd like to see happen, I'll move this up here. Let me move all of this up here. Or you know what, better yet, this is what I should do. Copy the problem. I'll put it down here. Okay, what I like is, I'd like for some of you okay, to try using this first point. I'd like some others to try the other one. So do whatever you want to do, but I'm going to give you a minute or two. Let's go 2 minutes and let's just plug. Some of you are going to use 1, 2, 14. The others are going to use -2, -5, -1. And then you're going to, crank everything out, distribute the ABC through, and then let's see if we get the same answers. 2 minutes. If you have an answer, and you feel like it, why don't you type the equation of the plane in the chat for everyone to see? And leave it as =0. So leave that constant on the left-hand side. I think you all can see each other's answers there. Remember, Hunter, to leave it as =0, right? Gotcha. Okay. All right, so what do y'all think? Are we getting the same answers here?
For the
Yeah.
most part.
Most part? Okay. Hunter, yours, we already said yours missing the equals. You got that, but.
I also didn't use the reduced version.
That's okay, though. That's the whole point, is that our answers might look a little bit different, but I guarantee they are multiples of one another somehow. Like if you divide through, you'll get to the other person's right answer. Okay, so it's kind of a nice fact. It doesn't matter what point you use, right? As long as you got the normal vector and you have a point on that plane, we should all come out with the same equation at the end. All right, we're gonna move on. All right, now let's talk about the angle between two planes. So if you have two planes, right? So I've tried to show the best I can here, two different planes, right? It's kind of a greenish one and a pink one. We've got these two planes. If we want to find the angle between those two planes, as long as they're not parallel to one another, then there should be some angle in there, right? Well, if they're parallel to each other, the angle would be 0. But if they're not parallel, then there should be some angle between them. And we'd like to get that, right? Does anybody have an idea of how we might be able to do that? Raise your hand or say it in the chat. See, Stephen, go ahead.
Use the dot product like we did from, I believe it was 1.4 to calculate the angle between them.
Yeah, so there's something with the dot product that allows us to calculate the angle between two vectors, right? But Stephen, what vectors am I supposed to be finding the angle between?
The normal vectors.
The normal vectors. Okay, so this is the part you have to kind of see or convince yourself of again, is that if I were to, each of these planes individually has a normal vector, right? So focus on the orange vector and the orangish pinkish plane. Do y'all see that orange vector is orthogonal to that orangish plane, right? And remember, it's a vector, right? So it can be anywhere, it can be moved around, but it is orthogonal to that plane. Similarly, the green vector is orthogonal to the green plane, right? So each of those normal vectors are perpendicular to those planes. Now what I'm going to do is I'm just going to move those normals around because like I said, you can slide normals around or vectors around, doesn't change what they are. So I'm going to put them together, right? Get rid of them like that. And when I put them together, this is the part you have to kind of see, is that the angle between the planes, let's see if I can do this. The angle between the planes, this angle right here, let's call it theta, is the same as the angle between these normal vectors, because the normal vectors are perpendicular to the plane, so they're off by 90 degrees, but both of them are off by 90 degrees. So you should, whatever angles between those normals should be equivalent to the angle between the planes. So that's what we need to do. To find the angle between two planes, we need to just use a formula that we learned 2 sections ago about finding the angle between two vectors. So I have an example for us to do here. Where is it? There we go. Find the angle between these two planes. We'll get back to the notes here in a second. So was it Stephen? I think it was Stephen. Stephen?
Yeah,
Where'd
it was.
Stephen go?
I'm right
There you
here.
are. I hate Zoom. Zoom, y'all are always moving around everywhere on my screen. I can never go back and track you down.
I also don't have a cam too, so.
That's fine. You're good. So look, we're going to try and find the angle between these planes. If you look back in our notes, we actually have 2 different ways we could have gone about this. In the last section, 10.4, we had this theorem for the cross product, and notice that in this formula, there's a theta in here. So we could, if we wanted to, solve for theta here by dividing both sides. Let me actually do it. We would take the magnitude of the cross product of the 2 vectors. We would divide it by the magnitude of each of the vectors separately multiplied together. That would give us sine theta, right? All I did there is divide both sides by the 2 magnitudes. And then you can take inverse sine on both sides. So there actually is a formula that looks like this. Does anyone have any idea why this does not appear in the textbook as a formula for us to use? Any guesses as to why?
Don't you have to have a calculator to find a arc sine?
Yeah, but yeah, we're going to need it even with the other formula. We're going to need it. We still need it for the other formula is right below it. See it right here? That's the one that I gave you this formula in 10.3. So we had a formula for theta. If you look at these 2 formulas though, which would you rather do? Would you rather do a dot product or would you rather do a cross product, right? So it's really just more because it's mechanically easier for us to do the dot product, and that's why we're just not going to use that. But in theory, we could use either one. There's another thing that should steer you away from the one involving the sine, and that's if you remember from pre-cal and other classes, if you do the inverse sine function and you get an answer, you have to check your answer and make sure it's in the right quadrant, because the inverse sine is restricted between negative pi over 2 and pi over 2. So if you get an answer like negative 30 degrees, you actually might have a different angle. It might be something else, might be in the second quadrant instead. You don't have that problem with cosine inverse because its domain restrictions, the angle is going to be between 0 and 180 or 0 and pi. And because of that, our 2 planes are never going to be anywhere other than 0 to 180 degrees apart, right? So cosine inverse is just the safer way to go. So I'm about to do this computation, but what do I need? Stephen said that we were going to figure out the angle using the dot product, using this formula, and we were going to be using the normal vectors to do this, right? So looking at each of these, I'm going to just look at that plane, and I'm going to find its normal vector. So I'm going to call it N1 for the normal vector of the first plane. That normal vector is just the coefficients on X, Y, Z. So very simple normal vector, 1, 1, 1. right? And then the normal vector on the second plane is the normal vector 2, -4, 7. All right. And then once I have those, oh my gosh, stop. Whoa. Okay, try this again. There. Once I have those, I'm going to go right here to this formula. Except instead of using U and V, I'm using N1 and N2. So theta is equal to cosine inverse of, okay, U dot V. That means I need to figure out what N1 dot N2 is. Remember, the dot product always gives you a number, right? So you just multiply these two together. 1 times 2 is 2. You add to that, these two multiplied together, that's -4. And then you add to that, these two multiplied together, that's 7. So what do we have there? 5. So we have a 5 in the numerator. And then we do have to get the magnitude of each of those vectors. So I do need the magnitude of N1, and I also need the magnitude of N2. All right, well, magnitudes aren't that bad with vectors. You're just going to do the square root of the sum of the squares of the components. Okay, so I get √3 on one of them. And the other one, what is that? 16 plus 420 plus 49, 69, √69. There we go. So we put these together. And that's just all a number, right? I can just get in my calculator and do this. And I'm gonna have a decimal answer, and I'm gonna make sure that my calculator is in degree mode, so our answer is in degrees. If you wanted to, you could leave it in radian mode, and then whatever answer you get is just in radians. So in my calculator, I'm gonna try and get this. If you have a calculator, go ahead and feel free in the chat to let me know what you get. I forgot to check if I'm in degree mode. Oh, well, I'll see in a minute. Ooh, I'm not in degree mode. Yeah, I was in radian. Try this again. Oh, I just deleted it all. I'll wait for your answer. So we got 169.66, and I'm assuming that's in degrees. Anybody else get that? Yep, we got a couple here. All right, looking good. So if we're given two planes, right? We're given the equation of two planes. The equation of two planes. It is relatively simple to find the angle between those two planes. Right? What if we dotted these two vectors and we got 0? What would we know about those two planes?
They're parallel.
Parallel? Careful. If we take a dot product and get 0, it means they're orthogonal. So I stopped here, the angle between two planes. I try to convince you that this next note says, hey, look, if two distinct planes, two different planes are parallel to one another, right? Then their normal vectors should be parallel as well, right? And we should expect their normal vectors to be parallel to one another, scalar multiples of one another. If the two planes are perpendicular to one another or orthogonal, like this, then we should expect their normal vectors to also be orthogonal, which means the dot product of those normal vectors should be 0, right? All right, so we did that problem. Now, moving on to a completely different topic, all right? Still talking about planes and lines here. We're now going to see how we can find the line of intersection of two planes. So in college algebra, you may or may not recall, is that, Jonathan, do you have a question?
Yeah, I had a question about
Yeah.
the answer of the last one.
Yeah,
For our homework and quizzes, do you want like the cosine inverse as an exact answer? Or should we type it into a calculator?
if
And
I'm
get the
asking for the
decimal.
angle, go ahead and take it all the way to an actual decimal approximation. Thank you for asking. All right, so if back in college algebra, or if maybe linear algebra, if you're in that class, if you have two planes living in three-dimensional space, let me get my planes out again. If you got two planes living in three-dimensional space, what are the possibilities? Let's talk about the possibilities of how these hit each other, intersect each other. If they're parallel planes, right? If they're parallel, they're never going to hit each other. And in linear algebra, that has to do with talking about consistency or consistent or non-consistent system of equations. So you may have that, right? You could also have that if they are not parallel, then they're gonna hit each other somewhere, right? And when they hit each other, it's going to form what object between the two? A line, right? It's going to be a line. Now I'm talking about two planes, not three planes. In college algebra or linear algebra, when you're doing a system of three equations and three unknowns, you're trying to find the intersection of three planes. I'm just talking about two planes right now. If I have two planes, they're either not going to hit each other, or if they hit each other, there's any tilt to one of them that's different than the other one, then we're going to have an intersection that is a line. And that's what we're about to investigate, is can we actually come up with the vector equation of that line? So I'm going to try and kind of like deduce it from a picture first, and then we're actually going to do it. All right, so here are two planes. They are not parallel. They intersect each other on a line. And I want to see if we can come up with the vector equation of it. So first, remember, each of these planes has a normal vector. You'll see the normal vectors to those planes. And here's the really cool part. Let's move those normals, because I can slide them around. Let's move them to where they're both at that intersection line. Okay, so those are my normals just moved around. Do you all see that if I cross those two normals, that vector lives on that line? Sorry, I should say it this way. That vector points in the same direction as that line. Every time, always. That is a very, very nice property. Given two planes that are not parallel, if you take the cross product of the normal vectors, the resulting vector is pointing in the same direction as the line of intersection of those two planes. Now, we needed two things, right? Two things to find the vector equation of a line. Two things. We needed a point and we needed a direction vector, right? Well, I'm telling you how you can find the direction vector by just crossing the two normals, and you'll get a direction vector. Now all you need is a point. Can we find a point of intersection of two planes? Well, all we have to find is any x, y, z that satisfies both equations simultaneously. So let me do this example, and then we'll kind of see how it goes. All right. Every time I turn off my screen share, my chat goes away, so I'll put it up here. All right, so I've got this example. Find the vector equation. So when I'm doing problems like this, and this will probably help you on your next mini exam too. When I'm doing problems like this, I always start by looking at what are they asking me for? So I'm trying to find the vector equation of a line, right? Well, if I'm trying to find the vector equation of a line, what is it that I need? To find the vector equation of a line, I need what? Two things. One, I need a point on the line. And then the other thing I need is a direction vector. This is from last class, right? Once I have those two things, I can use the formula RT equals the vector R naught plus TV, which was our main takeaway from last class, right? So
Professor, I have a
somehow
real
here,
quick question.
yes, please raise your hand.
Oh, sorry about that.
No, it's all right. I mean, just to be fair to everyone, I'm asking the same thing. So, but it's okay. Go ahead. Go ahead. What's your question?
I'm sorry, I don't know how. Anyway, so sorry about that. I thought it was when those two planes equal to each other when there's a solution.
When the two planes are equal to one another, there's a solution. Yes.
And that's
If we're trying to find a point on the intersection line, then we just need to figure out an X, Y, and Z that make both of those so that satisfy both equations at the same time.
cool.
Yeah, I think what you're doing is you're saying if you solve this like in linear algebra, right? If you do this like in linear algebra or something like that, then you can solve this system. You're going to get like a general solution. That solution, you can deduce what the equation of the line is from that. But it will not be the vector equation of the line. It'll be our standard equation like, you know, y equals mx plus b. What I'm trying to do is see if we can come up with a vector equation.
Gotcha, yes, sir.
All right, so I'm starting out with what I'm trying to find. I'm trying to find the vector equation of a line. What is it I need to do that? A point and a direction vector. Then I'll use that formula. So I start thinking about the two things I need, right? Let me go after the thing I think is easier first, which is the direction vector. So to get the direction vector, all I'm going to do is take the normal vector of the first plane and cross it with the normal vector of the second plane. And that should be equal to, I should have put it out front. That should be equal to what V is. V is the direction vector of the line, right? So I just have to cross the two normals. Now I didn't write down what the normals are, but I'll put them up here. The normal of the first one. Isn't this the same? Is this the same problem we just had? I think it is. So we've got that normal, and then we've got the normal of this one, which we're just peeling off the coefficients, right? 2, -4, 7. And here we're going to have to cross them, not dot them. So we haven't done that yet, right? We haven't had to cross those. Let's see if I can cross those real quick here. It was 1, 1, 1. Oh my gosh. 2, -4, 7. I still think that's faster than if I would have done it by hand. 11, -5, -6. 11, -5, -6. I left a space there so I could actually write down what I just did. I did 1, 1, 1, and I crossed it with the vector 2, -4, 7. There we go. And then from here to here, I used Wolfram to do this, right? But we can do it by hand, right? We can do it by hand if we needed to. All right, so of the two things I need, I've got one of them, right? I've got the direction vector for the line. I just now need a point, any point that lives on that line. So what I'm going to do to get the point is I'm going to try and find some X, Y, and Z that satisfy those equations at the same time. So I'm going to find an X, Y, and Z, which satisfies that X plus Y plus Z equals 5, but simultaneously, I need it to solve 2x minus 4y plus 7z. I'm going to say equals 10. I'm going to go ahead and on that second equation, I'm going to move that -10 to the right side. And now I have the joy of solving this. But I already know that there's an infinite number of answers, right? Because, I mean, it's a line, so it has an infinite number of points on there. I just need to find one of them. So I think what I'll do, and you have a lot of freedom here, I'm gonna go ahead and just say, let Z be 0. I'm going to actually force one of my points, one of my coordinates of my point to be 0, and I'm gonna hope that I can solve what remains. So if I let Z be 0, I have a new system. It's x plus y equals 5. And then I have 2x minus 4y equals 10. Because all Z being 0 did was killed off those two. That system of equations should have a unique solution. It is possible that it doesn't, but if it doesn't, I'll just pick a different value. I'll pick, y is 0 and go try and figure out what x and z are. So here I go. Let's see. I'm going to multiply. I'm going to do elimination here. And so I'm going to choose to multiply the top equation by -2. And you could do -2x minus 2y equals -10. Oh, crap. Is it not going to work? 2x minus 4y equals 10. And now we add straight down. So the x's cancel. We get -6y, right? -6y equals 0. Well, I think we're okay. Because the only solution to that is y equals 0. So now I know what y is. I already know that I let z be 0, which means I can solve for x now, right? I just take any equation I have up here. I'll take this first one. X plus y is 5. I'll replace y with 0, and that means x is 5. So remember, I wanted a point on that line. I found one. 5, 0, 0 is a point on that line. It's on the x-axis. Just happens to be, all right? You are not always going to have that happen. Just for this example, that's what's happening. If you did something else, right? Instead of doing z equals 0, if you said, hey, I'm going to let x be 0, or I'm going to let y be 0, you're going to get a different point than me, right? Right, we're not done. We're not done. We now need to take this formula that we had, right, from last class, and we need to replace the things here. We knew what V is, right? We figured out what V was. V was this. And we just needed R naught. And remember, to get R naught, all you do is use any point on the line and turn it into a vector. So I'm going to take the point we just found. I'm going to convert it to a vector and use it right there in that formula. So here's what our almost final answer is. R of t equals R naught, which is the vector 5, 0, 0, plus t times the vector v, which is the vector 11, -5, -6. That's one way I could write it. I could also write this as the vector 5 plus 11t, -5t, -6t. All I did there was distribute the t through and then add the two vectors together. And then I could also do the parametric equations. I could also do the symmetric, but I asked for the vector equation, right? That's what the question was asking for, the vector equation. So this is the vector equation of the line of intersection of two planes, of these two planes. Let me go to my notes here. So when I was doing this, when I actually wrote the code to make this little animation, right? Let me see here. Somewhere in here, I have that vector equation of that line. Where is it? Oh, did I use a different? Oh, I think I used different planes. Sorry. I used different planes. Never mind. I thought I used this. I thought that this image was the same planes as the ones in the example, but they're not. They're not. So strike that. All right. Moving on. The next two things I think are the most important. And I mean, you need to know how to do all this other stuff or you can't do anything after it. But these two results that we're about to talk about are like, to me, like, wow, okay. This would be hard to do, really hard to do without this little, I guess, formula that we're going to get. So let me first tell you what we're going to try and do. We're going to be trying to find the shortest distance between a point and a plane. So imagine that you have a plane, right, sitting in three-dimensional space. It's not necessarily the XY plane, so it's not flat on the ground. It might have some tilt to it. And you're trying to find the shortest distance between that plane and some arbitrary point. Can we do it? So I'm going to show you how we can do it. So here's a plane, right? Here's a plane sitting in three-dimensional space. You know, I can tilt it any way I want. So now we have some point that's not on that plane, all right? So we've got the point and we've got the plane. And what I'm trying to find here is the distance, the shortest distance between that point and that plane. What is the shortest distance? Yeah? Now, if the plane was the XY plane, like the ground, right? If it was the ground and I gave you a point, wouldn't it just be the Z coordinate of the point would be how far away you are? Right? But I'm not saying that. I'm saying this plane can be tilted. And if it's tilted, then it's no longer the Z coordinate. It's something else. And so we need to see if we can come up with a way of determining what that distance is. So let me show you how we're going to do it. It's going to rely on some stuff we've already talked about. So what you see in front of you, this plane and this point, that's given to you. You have that. That's the information that's provided. Here's the equation of the plane. Here's a point. Now, your job is to find the shortest distance. So here's how I'm going to do it. First thing I'm going to do is I'm going to find another point on the plane. Any point, any point. And because it's a plane, we should be able to find a point pretty easily because we just have to find an X, Y, and Z that satisfies the equation. So that should be pretty easy for me to come up with that point, right? Once I have that point, I'm going to generate a vector that goes from the point on the plane that I just found to the point that I'm interested in, all right? So I've got this vector now. The next thing I'm going to do is I'm going to calculate the normal vector of the plane. That's the vector that comes out orthogonal to the plane. There, right? Like this. I've got a normal vector. Now remember, that red vector can be slid around anywhere I want, right? That red vector is slid around anywhere I want. I have positioned it so that it actually goes through that point, the black point above, right? If I look at this from any direction, I've moved it so that that red vector goes right up through that point. I have the freedom to do that because the red vector is a vector and vectors can be moved around. Okay. The next thing I'm going to do is imagine moving the blue vector so that it is tail to tail with the red one. Okay, you see it? Move that blue vector over to where it's tail to tail. And then I'm going to get rid of the blue one here so you're not distracted by it. Go with me? Last step. I'm going to project the blue vector onto the red vector. Remember when we talked about vector projections? I'm going to project the blue one onto the red one. Boom. When I do that, I get a new vector that goes from here to there, right? Am I wanting to know what that vector is or how long it is? I want to know how long it is, right? So I'm trying to find that distance. That should be the length of the projection vector, which we called in a previous section the component of the vector projection. Or sorry, the magnitude of the vector projection is actually called the component. So here's the actual computation. You got to go back and look at the formula, right? There was a formula for the component of a vector onto another vector. Do I need to bring it up or are y'all good? Do I want to see it again or not? I see.
I want to see it one
couple
more time.
people want to see it. So let me see. I think it's 10.3. Let me see here. Where's this thing? 10.3. Yeah, dot product. So in 10.3, we had this thing where, here it is, where you have a vector and you drag this around. We were talking about, what does it look like to project the red one onto the blue one? Actually, we're doing it the other way around. We're doing the blue onto the red right now. So we're trying to find that vector and we're trying to find its length. So the formula for that, there's the projection. That's how to get the projection vector. And then to get the component. So if you want to know the component of u onto v, you dot v with u and you divide by the magnitude of v. That's the formula I'm about to use. But I'm using different letters because the blue vector here, right, is the one we are projecting onto the red. The blue vector is the vector that we came up with that went from one point to the other. So in this problem, we call that vector the B vector. And then the N vector is the normal vector. That's the one you're projecting onto. So that is this one. And then you divide by the length of N. So I'm going to need this formula right here. I'm going to copy it. And we're going to do an example. So what I just gave you was a formula to find the shortest distance between a point and a plane. Jonathan, what do you got?
Monica has had her hand raised.
Oh, I'm sorry. I'm so focused on this. Monica, what do you got?
Oh no, my question was just simple. From the vector equation of a line, the vector R naught, its components are always equal to the coordinates of a point on that line.
Any point.
Any point. Okay.
Any point.
I just wanted to clarify that.
Yep.
Thank
Yep.
you.
Thank you
Thanks,
for asking.
Jonathan.
Sorry, I didn't see it. Your hands are, when you raise them, are the little tiny little yellow dots I can barely see here. But yeah, thank you for letting me know. Okay, so I just told you how to find the shortest distance between a point in a plane. Look at what this is asking for, though. Find the shortest distance between these parallel planes. So visually, we have, well, let me go back up to where we had two parallel planes. Right here. Let's say we have two planes that are parallel to one another like this. And I want to know the shortest distance between them. So I'm trying to figure out, like, what is the distance? What is the distance between these planes, right? The shortest distance. Well, they're parallel, right? It's going to be the same distance no matter what, right? They should have the same exact distance. So all I need to do is kind of reformulate this question. And instead of doing it and treating it like the distance between two planes, I'm going to treat this one as my plane. We'll call it P1. And instead of that other plane, I'm just going to treat that whole plane as a point. And if I can find the shortest distance between that point and that plane, then I've found the distance between the two planes. So that's what I'm about to do. Maybe I can take a copy of this. Yeah, let me take a copy of this and take it over to where we're working so I can visually show you everything that's going to happen. All right, so just for the sake of simplicity, let's call the plane down on the bottom. Let's call that plane 1 and this one plane 2. It really doesn't matter if I've got those in the right order, because remember, in three-dimensional space, you can just move around, it'll look different, right? So just for simplicity, let's call the bottom one, the green one, plane 1, and the top one, plane 2. So I need to first find a point on the second plane, a point on plane 2. So any X, Y, and Z that we can come up with that would satisfy that equation. And I've got a pretty simple one. How about 10, 0, 0. Right? If I plug in 10 for X, 0 for Y, and 0 for Z, that equation would be satisfied, right? So that in fact is a point on that plane. By the way, the most common mistake or the most common wrong answer I get on this, on a problem like this, is students, what they'll do is they'll take this problem and they'll first divide everything by 2 here. And they get this. Do y'all see all I did was took the second equation, divided everything by 2, and I got this? And do you see that the plane 1 and plane 2 almost look exactly the same? And they say, oh, this is 5 and that's 10. So then they tell me the distance between them is 5. And that's completely wrong. Because these planes are not flat. Again, it's not, they're tilted. And so it doesn't work that way. All right, so I found a point on the second plane, right? Now I'm going to try and find a point on the first plane, any point I want. So any point I want down here. So now I'm trying to satisfy that. Hey, I've got a nice one. How about 5, 0, 0? We agree that that satisfies the first equation? Yeah. Okay, once I've got that, I'm going to create a vector that goes from plane 1 to plane 2. That will be the B vector in this formula that I'm going to use. Okay, it's the B vector. And so B for us is the vector 5, 0, 0. Right? It's the vector that goes from the blue point to the black point. Questions there? Now I'm going to create the normal vector of this plane, that normal vector, right? I need to find that. That should be easy because I have the equation of the plane 1, don't I? And so I'm going to use the normal vector, which is just the coefficients on plane 1, 1, 1, 1. And then this is the part that's kind of weird, but we're saying move that n to where it lines up with the black one, okay? And then move the red one over to where it they go tail to tail, right? And then when you project the red one down onto the normal vector, you will find this projection vector right here. And then the length of that is the component. And that's the distance between the two planes. But in all, I just have to do that computation right up here, top right corner. I need to dot these two vectors and then take the magnitude of that answer and then divide that by the magnitude of the n vector. And that should be the distance. So let me go ahead and dot the two. Does it matter what order I dot them in? Dot product doesn't matter, right? So it doesn't matter which way I do it. I'm going to do n dot b. I'm going to write it n dot b like this. That will be, I'm multiplying those, that's 5. And then 0 and 0, right? Plus nothing is 5. And I'm supposed to take the absolute value of that, but absolute value of 5 is just 5. So my numerator is 5. And now I need the magnitude of the normal vector. Now that I have to, because it's a vector, I have to do the square root of the sum of each of the components squared. So sum of 1 squared plus 2, 1 squared plus 1 squared, that's root 3. And now just plug into the formula right here. That will be equal to 5 over the square root of 3. That's the distance between those two planes. That is the distance between those two planes. It is also the shortest distance between that point and the plane, however you want to look at it. All right. Do I have any questions? Oh, Jonathan, yes.
If the Z and Y positions are 0, and they're parallel, wouldn't they just like be laying on top of each other?
If the Z and the Y,
Like
Oh,
the
yes,
2
yeah.
points you chose.
yeah, I chose.
So why isn't the distance just 5?
Hold on, I'm gonna try and, okay, so I understand Jonathan's question. I think to help everyone else, in case you don't understand it, do it this way. Here. It's a great question. Okay, let's just say that's my X, my Y, and my Z axis, right? You know what? Let's change it up a little bit so it's easier for me to draw. Let's make this the, oh, what's going on? Come on, stop. There we go. Like that. Okay, so you were saying that the X and the Y, or sorry, the X, what was the point? Go back and look.
It was the Z and the Y.
Yeah, but okay, so the X, it was 10 and 5, right? 10 and 5. You're gonna have to let me kind of move this around a little bit. All right, so what we did is we picked 2 points, right? The first one we picked lies on the green plane. That's the point 5, 0, 0, right? The other point lived on the other plane, and that was the point 10, 0, 0, right? Do you see that the distance between those two is not the distance between these 2 planes? Does everyone see that? It's that there. I'll tilt it just a little bit. There we go. So what you're talking about, I think this is what you're asking me, is that, you know, shouldn't this distance be the distance between the 2 planes? No, because we're actually talking about this distance from here to here, right? Does that clarify, Jonathan? Now, if these 2 planes were, again, like, if these planes went through the XY plane or through the YZ plane or the XZ plane, if they were actually parallel to those planes, then it would just be as simple as the difference between coordinates, right? If you reorient this, let me clear all this out. If you reorient this thing, where when you look at it, this is your x-axis, this is your z-axis, and let's say your y-axis goes backwards that way, right? We're looking at it from straight on. Then if I want to know the distance between these, all I need to know here is the difference in the z coordinates, right? Then that would be your answer. But as soon as you tilt them, it doesn't work anymore. Any other questions? Okay, moving on. So we now know how to find the shortest distance between a point and a plane, which can also be used to find the shortest distance between 2 parallel planes. And now what we talk about is the shortest distance between a point and a line. Between a point and a line. So imagine you have a line in 3-dimensional space, all right? In 3-dimensional space. You got this line, you probably have a vector equation for it, right? You got this line. And then what you have is a point sitting somewhere else. And you're trying to find the shortest distance between the 2. That generally in 3-dimensional space seems like a very difficult problem. So I'm going to try and convince you of this again with like an animation. This animation is going to look like I'm doing it in 2-dimensional space, but I want you to remember that we are in 3-dimensional space. So it's kind of like, let's see here. If you imagine just a line in 3-dimensional space and some point somewhere, then there's a way that I can move my head around to eventually make it look like this picture, right? Like I can move around in space and kind of tilt my head, and eventually it would look like this. if I just get myself in the right position. So even though, again, this looks like it's on a flat sheet of paper, think about it as living in 3 space. So I've got my line and I've got my point. That's given to you. Okay, you're given that information. Here's a line, here's the point. Now go find the shortest distance between the two. So I am trying to find this distance right here, right? I'm trying to find that distance. What is it? Okay, here's what I'm gonna do it. First, I'm gonna pick a point on, I'm gonna find a point on the line, which I should be able to do because I have the equation line, so I should be able to find a point. Then I'm gonna find another point on that line. And from those 2 points, I will create a vector, A. Now, just so you know, if they give you the vector equation of the line, the vector equation of the line, then V, remember V is the direction vector, it would be okay to use V for A here. All right, A could be replaced with V here if you were given the direction vector in the vector form of the line. But if you're only given like the algebraic equation or something, then you might have to come up with 2 points and then create the vector. You'll see when we do an example. So we've got this point, we've got this line, we've got the direction of the line, calling it A. Now what we're going to do is we're going to create a new vector that goes from any point on the line to that point that we were given P, and we're going to call it B, just like we did in the previous example. And we are looking for this distance right there. And we're going to use a little bit of trig now. See, what we don't have here that we had in the previous problem, we had that normal vector. Remember, right? We had that normal vector from the plane and we could project onto it. With a line, there is no normal vector. So there's nothing we can project onto. So instead, we're going to look at this purely as a trigonometric problem. And we are going to look at this angle between the 2 vectors, right? That angle theta. We should be able to find the angle between 2 vectors, right? The vector B and the vector A, they have an angle between them. We have a way of finding that angle. But more importantly, we've created a right triangle, right? In this right triangle, if we want to know what D is, we can just use the definition of sine, right? Sine of theta would be the opposite over the hypotenuse. So I put sine of theta is D over, and notice I use magnitude of B here because remember, B is a vector. If we're looking at this as a right triangle, and we want to know what D is, and this is theta, then we need to be looking at this as the magnitude of B, not B as a vector. So do y'all agree? Just nod your heads yes or no. Do y'all agree with that statement? Sine of theta should be D over the magnitude of B. Yeah. And we just don't know what D is, right? We're going to try and solve for D. All right. So that's where we are. Let's see what we're going to do with this. We're going to take that equation. Let's just multiply magnitude of B on both sides of this equation. If we do that, it cancels on the right. And we get magnitude of B sine theta equals D, right? Or you could write D equals magnitude of B sine theta. Y'all good? I'm about to do something pretty awesome, okay? Let's just think back. The vector B is just a vector between a point on the line and the point we're given, right? That should be pretty easy for us to find, right? If someone gives us a point and they give us a line, we should be able to find a point on that line, and then the point we're given, we just create the vector. So B shouldn't be that much of an issue for us. But how about theta? Isn't sine theta going to require some work from us? We're going to have to go through some using, maybe the dot product thing that we used earlier and go find theta. That's going to be a pain in the ass. So I look at this and I realize, hold on a second, time out, time out, time out. This right side, why is that not working? Looks a whole lot like something I've seen before, doesn't it? It looks like the magnitude of the cross product. right? We have a formula that says this. If you take two vectors, u and v, and you cross them and then take the magnitude, it's the magnitude of u times the magnitude of v times sine of the angle between the two vectors, right? This right side looks a lot, right? Like this, but it's missing something, right? It's missing in front of this, the other vector. What other vector am I talking about in this picture? Theta is the angle between the two, right? So what vector am I talking about?
A.
A, right? We're talking about the A one, right? So watch, I'm going to do something really cool. I'm going to just multiply both sides of this equation by the magnitude of A. I'm allowed to do that, right? I can always multiply both sides of an equation by some number as long as it's not 0. If I do that, what does the right-hand side become now? Just the magnitude of the cross product, right? That's this formula right here. So now I have magnitude of A times D equals the magnitude of the cross product of A and B. Oh, not over. Next line, I'm going to do that. Now I'm going to divide both sides by the magnitude of A. So D will be the magnitude of the cross product of those vectors over the magnitude of A. Bam. That's it. That's my formula. So in order to find the shortest distance between a point and a line, all I need are two things. I need a vector going from the line to the point. That's the vector B. And then I need a direction vector of the line. That's the vector A. Once I have those, I just do that computation, I'm done. It's pretty awesome. It's pretty powerful because you don't have to do anything with angles, nothing. Everything is just some cross products and some magnitudes, and you're done. All right, all of that's written down here. You have it right here. Okay, there's the formula for it. And right here, there. So we get to our last example here for this section.
Real fast.
Yep.
With that one just now, so A was the direction vector of the line.
Yes.
Okay, and B was the vector between the vector from a point to the point, right? A point on the line to the point we're trying to find the distance to.
Exactly.
Gotcha.
Perfect. That's perfectly said. Yep. The vector A is the direction vector of the line, any direction vector of the line. Vector B is the vector going from any point on the line to the point we were given. All right. Why don't I give you an opportunity to work this out yourselves, and I'll do breakout rooms. I'm not real big on doing this type of thing, but since we're doing Zoom, let's go ahead and try it. I don't want to overload you. It's only going to be like 2 or 3 people in each room. All right. If you're like real adamant that you don't want to participate, then you don't have to. All right. You can stay here. I'll be back.
Could you throw those breakout room invites out there again? Oh, he's not here.
I'm sorry, what did you say? I stepped out
Oh.
to get a drink for refill.
Could you create those breakout rooms again?
Did it
'Cause,
not?
well, you can't see the question when you go to the breakout room.
Okay,
So I jumped in there and then none of us knew what the question was, so we all left so we could get the question. So the breakout room's gone.
Hunter, if you hit the breakout room button on the bottom of the screen, it should give you the option to go back into that break room.
yeah,
Awesome.
see if it does,
I
because I
see it.
don't see a way to throw you back in.
Yep, I see it. Thank you.
Okay.
Thanks, Georgia.
No problem.
For those of you who are still here, I'm just gonna work it out. But silently work it out myself. you can just give me decimals for your answers. I'm just going to go another maybe 2 minutes. Does anyone here have questions? Just get a decimal. If you can, just get a decimal answer. You don't need to give me an exact. Okay, we should be getting everybody back in here now. So if you got an answer as a decimal, type it into the chat and let's see what we're getting. Let's see
So,
if anybody.
question, that's the magnitude of the cross product on the top?
Yes.
Cool. Give me a sec.
We've just got a few more minutes. So let me show you what I did while you're maybe still calculating. I wrote down, I drew my line and I put the 2 points that were on that line, and then I drew my point here in green. First thing I did is I created a vector that went from the 1 point on the line to the other. I call that A. So I just created the vector the way we create vectors from points. And then I created another vector I called B, which goes from either one of these points. I didn't have to use this one. I could have used this one, gone here to here, doesn't matter. But I went from here to here, created a vector. And then once I did that, I took their cross product. And I did that using Wolfram Alpha. And this is what I got, it's huge. And then I had to find the magnitude. So just so y'all know, on Wolfram Alpha, if you type norm, and then you put in, it looks like like an ordered triple, like a point, but if you put that in, it's going to treat that like a vector, and it will give you the length of the vector. So in Wolfram, norm means length of vector. So it gives me the length, just FYI. So I did that in Wolfram, and I got 97.765. So that's the numerator of the D over here. I took the cross product of the vectors and I took the norm or the magnitude. Then I took the vector A and I took its norm on Wolfram and I got 8.775. Then I did this on my calculator to divide the two. I got 11.14. Any questions on that? Christian?
So I scaled the vector A cross B, and I got I scaled it by 3. But if you multiply the answer that I got by
What do you mean
3,
you scaled the vector?
like A cross B is the -87, -33, -30.
Okay, okay. You can't scale it.
Why?
Well, because this is not a normal vector to a plane where it doesn't matter. See, because what we want to know is what the length of that cross product is, right? And if you scale it, you're changing its length. So in this particular case, if we're going to use this formula, you are not allowed to scale the A cross B. I'm glad you did that though, because that way I could let you know it's not okay, right?
Yeah, I appreciate that. Thank you.
Yeah. Nicholas?
On the topic of scaling, is it all right if we scale it, but we bring the scale on the outside of it?
Yes,
Like
that
say we
you can
scale by a
do.
third, but bring it out, just simplify.
Yeah. You can do
Okay.
that. Yes.
Gotcha. Thank you.
Yep. Hunter?
If there was something like this on like a quiz, would you want it in that decimal form or would you want it in the awful square roots over each other?
Decimal.
Decimal?
Yep.
Significant figures? Just
Whatever.
like out to 2 or 3?
Yeah, we're not building a bridge or anything right now.
Gotcha.
So. Okay, so I know it's time and we need to go. We are on track of where we need to be. Next class, we will hopefully be face-to-face again. But we will be talking about quadratic surfaces. And I will not need the whole day for that. So this quadratic surfaces should only take half the class. We will actually get into vector functions and space curves next time, which is good because your mini exam 2 that I just sent you, it goes up through 10.7. So by the end of next week, no, by the end of end of next week for sure we'll be through 10.7 by the end of next week. On your mini exam that I sent you, last thing here, I promise. I'm just going to tell you right now on that exam, there's only 5 problems. In theory, right now, you can do the first 3. You have everything you need to do the first 3 problems. The only thing you can't do are the other 2, because this is vector functions and we just haven't talked about it yet, right? So if you want to get a jump on that, even though you still have another one that's due when? A week from today?
Yeah.
Yeah, you already have everything you need now for that one as well. So yeah, that's it.
Appreciate you
Okay,
releasing
everyone
them
have a good
early,
day. I'm gonna, if you need, go ahead. If you need to leave, you can. Lewis?
Oh, appreciate you releasing them early though. That really, really helps me a lot.
Yeah, I'm gonna try and get them out so they give you at least like 2 weeks for each one. But a lot of it's gonna depend on whether or not we stay on the schedule of what we're supposed to do. If that's the case, then you should have some time with
Is
each
class
one.
functioning the way you wanted to?
Pardon?
Is class functioning and operating the way you wanted to at this moment?
Today went okay, I guess, but you know, we'll be back in the class next week, so we'll see how it goes.
Sweet.
Good.
I have a quick question.
Yeah, if you need to go, you can go. I'm gonna stop recording. But